Hello, my name is Sebastien Ballado, and this is my project on car suspension systems. So as an introduction, car suspension systems can be modeled using Newton's second law, and we can also use numerical methods and differential equations to model the effects of the road on suspension systems. According to the article that I used, we were able to come up with a simulation model for specifically one suspension system. So, for example, a quarter car specifies um, 1/4 of the car, so for one wheel, and there are four wheels, so this is 1/4. Um, so we're able to come up with this model for the mass, spring, and damper model. So we have the first mass, the sprung mass, the second mass, the unsprung mass. Then we have the spring connecting those two and a dash pot. And we also have the KT as the stiffness of the tire, and this is the function for the road. So we were able to come up with these two equations using Newton's second law. So this is for the first mass, and this is for the second one. So we're using that, we are able to create this block diagram. So here we have x1 double dot, or acceleration of x1, then integrate twice, and then you should get these values. It loops around, and then we get back here. And then we have the two scopes for x1 prime, x2 prime, and x1 and x2. And I also decided to graph the function of the road, xt, as we see in the original equation. The author used sine t for xt as a model of the road for analysis purposes. And from this, we were able to plot x1, which is this yellow-green line here, x2, which is this blue line, and also here, xt, which is the model of the road, the dotted red line. And we can also plot x1 prime and x2 prime and how that changes with the road. You can see as the road goes up, so do the speed as well as the distances of x1 and x2 go up, and they follow this curve here. Going back to the model, we can change a few things. We can change the model for the road, which is xt, and as well as the other constant values like stiffness of the spring, stiffness of the tire, the dash pot, damping coefficient, the two masses, and the force between the two masses. And I decided that to display the effects of changing xt and k values. So first up, we can change xt and see how that changes. So originally we had xt equals sine t, and I changed it to xt equals e to the t, and you can see how that changes with x1 and x2. It follows the road pretty normally. And then here, for changing k is also known as the stiffness constant between the two masses, and originally we had a value of 5,700 newtons per meter. I decided to experiment with lowering it, and lowering the value of k represents a softer suspension, and we should expect that the values of x1 and x2 should change more with the road function. And we can see here the original 5,700 Newton per meter with sine t, the original road function, and changing it to 1/10 of this, we can see that the change in the differences between x1 and x2 are much more dramatic and less sensitive to the road function. So as see, there is a bit of delay here as the road goes down, between the road going down and the change of the distances x1 and x2 going down around here. And in conclusion, we can model car suspension systems with differential equations and can predict how that will change based on stiffness, mass, and road functions.